Welcome back everyone. In this lecture we will prove complete reducibility for finite dimensional representations of SL2. So, let me recall what we have done so far and then we will actually get into proving this complete reducibility. So, I will begin with recalling some of the ideas that we have seen in earlier lectures. Okay. First thing is so, it does not matter like whether you work with SL2 or any Lie algebra. Okay. So, let us say G is finite dimensional Lie algebra over complex numbers. So, then we have some information about irreducible representations of G. Okay. So, let us say V is finite dimensional irreducible representation of G. So, then what one can do, one can actually talk about given a subset, okay, sub-representation generated by that subset. Okay. So, that notion one can define for any representation, not a problem. So, let me just define it here on this side, okay, and then we will use it here for the irreducible representation. So, you take W to be finite dimensional representation of G. Suppose let us say I have given a subset S of W. Okay. So, then I want to talk about sub-representation of W generated by S. So, I want to talk about this. So, what is this? This is the sub-representation of W generated by capital S. So, what it is? It is actually basically by definition you can take it to be intersection of all sub-representation that contains S. Okay. So, you can take it to be intersection of all W dash where W dash is G sub-representation and S is contained in W dash. So, it is not hard to see intersection of any family of G sub-representation will be again a sub-representation, and if S is contained in W dash, then it is clear that S will be contained in W dash, okay, intersection of W dash. So, in particularly this sub-representation of W generated by this S is the smallest sub-representation that contains S. Okay. This is the smallest sub-representation of W that contains S. Okay. So, now let us specialize to this finite dimensional irreducible representation. Okay. So, maybe I will actually state one exercise which is actually very nice. Okay. Maybe that one can do it for first some singleton S and then you can do it for any general S, not a problem. So, what is exercise? Suppose S is some singleton V. So, let us say this is sitting inside W where W is representation G representation. So, then we talk about this sub-representation generated by this V. Okay. This is the sub-representation generated by V. So, how one can get as a space? Okay. So, this is actually exactly if you think about it, you can take any elements of G and then act it on V. Okay. So, then that element must be again part of this sub-representation generated by V. Okay. What I mean by that? If I take xi1 etc. xik coming from G and then if you apply xi1 on xi2 and so on xik of V. Okay. Then this must be actually element of your sub-representation generated by V. Okay. But if you think about it, the span of this will be again submodule. So, that will be exactly your G sub-representation generated by V. Okay. So, what I want to say? So, I claim that see this sub-representation generated by V. Okay. So, this is the exercise. So, So, this is spanned by all possible words. Okay. So, you are sequentially applying, maybe I will write it clearly. So, you take x I 1, apply it on x I 2, apply and so on, x I m applied on V. Okay. You take all possible things where this x I 1 etcetera, x I m, they are all coming from G. So, now we can allow m to be actually 0, so that you can actually have empty word. Okay. So, this you allow m in G plus. So, when m equal to 0, you get this whatever this is on the right side to be just V. Okay. So, in that sense you can see that this sub representation of this W generated by V is given by the span of this. So, first of all, by taking m equal to 0, you can get V in this sub representation generated by V. Okay, and it is clear that if you call this is right hand side, then the right hand side should be subset of this V. Okay. So, this is easy to check. For the other side, so you need to verify what is on the right hand side is actually G sub representation. But if I take any x in G and then if I take any V in this any W in this right hand side, sorry. So, we will check. So, let me write properly. We verify the right hand side gives us G sub representation. Okay. So, you start with this right hand side, take some W in W, W in this, and then for any x in G, what we need to verify? We need to verify x dot W should be in this right hand side. But what is W? So, W will be some combination of this x I 1 acted on x I m of V, okay, where this I 1 etcetera I m will vary. So, it is just a finite sum. So, to prove that x dot W is in right hand side, it is enough to prove that x dot x I 1 etcetera x I m of V, this is inside right hand side. But if you think about it, this is just a word with one extra term. Okay. This is just some y I 1, y I 2 etcetera y m plus 1 of V, where y is are all coming from your Lie algebra. So, that says that this sub representation generated by V is nothing but span of all these elements theoretically. Okay. So, it is not hard to generalize this exercise to actually to other subsets. For example, if you take S to be just a subset of W, where W is given G representation. So, then what will be the sub representation generated by this S. So, this will be just all possible combinations. Okay. You take span of over C and then now you apply x I 1, x I 2 etcetera x I m on some V s, okay, where V s is also varying and this m is also varying and this I 1 etcetera x I m, they are also varying. Okay. So, in that way you will be able to get all these elements of this sub representation G sub representation generated by capital S. So, this is in some sense implicitly used in understanding the finite dimensional irreducible representation of SL2. But the thing is because this SL2 is actually very small Lie algebra and the commutator relations are very explicit. So, that is why we were able to make very specific choice of basis of this finite dimensional irreducible representation of SL2 on which the elements of this SL2C acts like some very explicit way. So, that was possible for SL2C. So, now if we go back to our original question, okay, what we can say about given any finite dimensional irreducible representation of G. So, if you take V to be any finite dimensional irreducible representation of G, then if I start with any V non-zero inside capital V, then it is clear that I can look at this sub-representation generated by V, because this is going to be non-zero sub-representation. So, this has to be entire V. So, this also forces that, using our earlier remark, this V has to be span of all these elements xi1 applied on xim on V, where this m is from G plus and then this xi1 etc. xim coming from G. So, with the convention that when m equal to 0, this xi1 etc. xim on V is just V. So, this is the convention. Okay. So, when m equal to 0, this corresponds to empty word. So, this you get V. So, this is somewhat very useful information about finite dimensional irreducible representation. Okay. Later, if we get time, I will actually talk about what is called this PBW theorem for universal enveloping algebra of G. Okay. So, there we will be interested in establishing a basis that looks like this. Okay. So, using that particular basis, PBW basis of this universal enveloping algebra, we will be able to get very specific spanning set for this irreducible representations of G. And then it is actually a very interesting question in representation theory, that whether one will be able to actually come up with a nice basis that coming from this PBW type spanning set. Okay. So, yeah, I need to introduce that universal enveloping algebra and so on. For that we will actually do that in some other class. But it is now it is clear to understand this finite dimensional representation, irreducible representation of G, we need to understand the successive or application of these elements of G on some single vector V. But the thing is, this G in practice could be like very large Lie algebra. Okay. For example, we can restrict ourselves to only a basis of G, but if the dimension of G is really big, then we have lots of choices for this exercise. So, then we end up getting really lot more elements. Okay. So, then that makes it actually kind of very difficult to handle this spanning set. Okay. So, I am not claiming that this spanning set will be somewhat easier to handle, but in SL2 theory we saw that this spanning set is actually somewhat nice. We got very nice information about by replacing this generating vector by some suitable vector called maximal vectors. Okay. So, now let us move to this complete reducibility of finite dimensional representation of SL2C. So, let me recall the definition of complete reducibility. Okay. So, a finite dimensional representation V is called completely reducible if V can be written as direct sum of finitely many irreducible representations. So, as I actually written here, I am not talking about any particular algebra or anything. So, you can see that this completely reducible one can define in any category of representation over any algebra. Now, if you are interested in SL2 representation, you start with finite dimensional representation of SL2 and then you demand this V can be written as direct sum of irreducible representation of SL2. Okay. So, let me recall what we did for finite dimensional irreducible representation. So, if V of D, if you take, okay, this is a finite dimensional irreducible representation of SL2C. So, we saw that the operator H acts on VD diagonally, okay, or semi simply, and this operators XY, they act on VD nilpotently. Okay. So, these things we already observed. So, if we actually have this complete reducibility, then what will happen? So, using these using this remark, we can easily see that H should act on any finite dimensional representation of SL2C as semi simply or diagonally. Similarly, X and Y also should act on any finite dimensional representation of SL2C nilpotently. Okay. So, from this plus using this complete reducibility, so we can get H acts diagonally or semi simply on any finite dimensional representation of SL2C. Similarly, X and Y act nilpotently on any finite dimensional representation of SL2C. Okay. So, this is somewhat a hint to actually how to go about proving this complete reducibility. So, we will come to this later, but before that here are some general remarks about how one can actually deal this complete reducibility, or even like this problem of breaking any representation into some smaller representation. So, this is a very important idea, actually one actually sees in even in linear algebra. So, that is the idea one can generalize even in the representation theory. It does not matter whether you are working with groups or algebras, associative algebras or Lie algebras. So, you can actually use these ideas, okay, what I am going to talk about now in order to break given representation into some smaller representation. So, let us see what is that idea. So, let us say you have an operator T, okay. Let us say some algebra G is acting on V, okay, just say G acts on V. So, just for simplicity again we will assume dimension V to be finite dimensional, okay, finite. So, if G acts on V, you can take it to be G Lie algebra, not a problem. So, now you have some operator, let us say T, which is inside endomorphism of V. Okay. So, this T is an operator from V to V. So, now assume that, so these are all hypotheses, okay, this is all assumption. So, there exists this operator T, and then this operator actually commutes with the action of G. So, what is the meaning of that? So, let us say the action is given by this map phi. So, phi is a map from G to this GL of V. So, given x you have phi x. Okay. So, T commutes with the action of G means if you take this phi of x and then if you consider this map T, they commute with each other. So, T phi of x is same as phi of x T, and this is true for all x in G. Okay. So, this is what I mean by T commutes with the action of G. So, in this case what we can do, we can actually, so because T is given to be a linear operator on capital V, we can talk about eigenspace decomposition or generalized eigenspace decomposition. Okay. So, that is at least exists. So, for example, you can talk about primary decomposition or cyclic decomposition and so on. But the thing is, let us see what is useful for us. So, I would say for us primary decomposition will be much more useful, because in the primary decomposition or otherwise this generalized eigenspace decomposition, each invariant spaces are given by kernel of this polynomial in T operator. Okay. So, let us make this remark. Okay. This is simple exercise, maybe I will leave it as exercise. So, what I want to say, suppose if I take a polynomial in T, okay, and then look at the kernel. So, then this will be a subspace of V. Okay. So, let P of x inside your C x and consider this P of t, which is a map from V to V. So, then we can talk about this kernel P of t. Okay. So, this is going to be a subspace of V. So, this is going to be a subspace of V. So, now what is my claim? My claim is this kernel P of t must be G invariant or G submodule of capital V. Okay. Because this information T commutes with phi of x, that makes T actually G module homomorphism from V to V. So, in particularly this P of T. So, this is also will become G module homomorphism from V to V, because P of T also will commute with the action of G. So, that makes this kernel P of T as a submodule, okay, or otherwise you can check directly, there is no issue, but this is the reason, because T commutes with phi of x for all x. So, that will imply P of T also will commute with phi of x for all x. So, that makes P of T this map as G module homomorphism. So, that way we get this kernel P of T as a G submodule. So, now in particularly if I write V as direct sum of this generalized eigenspaces. So, this means direct sum of let us say theta, where theta is coming from C. So, this is direct sum notation. So, where V theta is generalized eigenspace, let us say those vector V in V such that T minus theta identity power some n V, okay, on V is 0. So, it is actually simple exercise from linear algebra. So, even though you vary this n V, okay, so you can actually prove that. So, there is a unique capital N such that this V theta will become a kernel of T minus theta 1 power capital N. Okay. So, this I will leave it as exercise. So, this is not hard, but anyway. So, you can actually talk about this what is called this generalized eigenspace. So, now we have this decomposition of capital V into this direct sum of generalized eigenspace. So, this is called this what is called primary decomposition. What is important in the primary decomposition? All these V thetas which are occurring in this decomposition, they are all kernel of some polynomial in T. Okay. In particularly from this earlier remark, this V theta becomes G submodule of this capital V. So, in particularly we have written this V as direct sum of G sub representations. Okay. So, what we were interested in? We were interested in breaking down this capital V into some smaller representation. So, basically what actually this procedure tells, if you are able to find, okay, so what is the strategy? So, the idea is, okay, find element T in endomorphism of V such that T commutes with the action of G. So, then this V into direct sum of this V theta, theta in C. So, this is going to be all G sub representation. Okay. So, this is one way to actually break down V into direct sum of smaller G sub representation. So, this is the idea that we are going to use now in order to prove this complete reducibility for SL2. For that we need to find given this SL2 action of V, okay, we need to find an element inside this endomorphism of V such that that actually commutes with the action of SL2C. So, if you think about it actually so one can actually how one guesses this element, this is just by computation one actually can guess this element. So, we have to use only the information about SL2C in order to find this element. Okay. So, this is where we actually define what is called Casimir element. Okay. So, here is the definition of Casimir element, but again Casimir element is motivated from the above discussion. Okay. You are supposed to find some element inside this endomorphism of V that actually commutes with the action of SL2C, that is why you need this Casimir element. So, let us say V is finite dimensional representation of SL2C. What is this Casimir element? This Casimir element is actually element of this endomorphism of V that is given by xy plus yx plus h square by 2. Okay. So, maybe as an operator it is just you can think like okay, this C of V to be x y of V. Okay, maybe let me use this representation notation so that it becomes more clear. So, let us say this phi is the representation that is actually given from SL2 C to this endomorphism of V. Okay. So, then what is this C? C is nothing but you take it to be phi x, phi y plus phi y phi x plus phi h square divided by 2. Okay. So, then this is an element of endomorphism of V. Endomorphism of V is an associative algebra. So, this all product addition everything makes sense inside endomorphism of V. So, now it is easy to check this C that we have defined, it is actually commutes with action of SL2C. For that we need to check what will happen if we apply with C bracket phi x and then C bracket phi y and then C bracket phi h. So, all this should be 0. So, it is enough to do only the first two because phi h is nothing but phi x phi y, the bracket of this. So, if something commutes with both phi x and phi y, then it will commit with the leap commutator bracket. So, this one will come for free. So, let us try to prove this. So, I will verify only the first one. So, this one. Okay. Let us take C phi x and then compute what it is and then we will see explicitly this is actually 0. So, the bracket C phi x then this is nothing but we can start ignoring phi if you want, but anyway I will write it. So, phi x phi y plus phi y phi x plus phi of h square by 2 comma phi x. So, that is what this bracket. So, if you do the computation very explicitly, so first you take the product between them. So, phi x phi y phi x plus phi y phi x square plus phi h square by 2 phi x, then minus phi x square phi y minus phi x phi y phi x minus phi x phi h square by 2. So, note that. So, this term phi x phi y and this phi x phi y phi x they get cancelled and we need to cancel others and then see what we get. Okay. So, now if you think about it, so what is going to happen with if you maybe we keep one of them and then try to commute others. Okay, just take this phi x, phi y, phi x square and then keep it as it is. Maybe this we can commute and then see what is happening. So, you get phi h by 2 and then phi x phi h minus, okay, so the bracket of those two, which is the bracket phi h phi x. So, then that is going to give us, so this term that I am computing. So, this is the term, let me call it 2, okay, the term 2 is, if you take it to be phi h by 2 phi h phi x, you replace by phi h phi x minus this, and then here this phi h phi h by 2 will stay. So, then you can see that, so this is exactly equal to phi h by 2, again phi x phi h minus phi h by 2, h x is 2 x. So, this is phi x times 2. Okay. So, now if you just switch these two, so you can take 1 by 2 out, then you get phi x phi h square, okay, and then minus 1 by 2 the bracket phi h phi x phi h minus phi h phi x. Okay, then you can see that, so this is going to give you 1 by 2 phi x phi h square, and then this is going to give you 2 x. Okay, so minus, so if you put 2 x there, you get phi h phi x phi h and then minus phi h phi x. Okay. So, this is the term 2. So, this term 2 has this of phi h phi h square. So, that is going to get cancelled with this. So, then what remains is this. So, this is you can actually take it to be, okay. So, you add and subtract and then you see that, okay. So, yeah, we need to actually identify with this. So, we will take it to be this and then see. So, the left hand side, which is this C phi x, okay. C phi x is equal to, this is the term 2 which we are writing. So, this is already there, this is also we need to compute, okay. Phi y phi x square, and then if you use this, this is let us say minus. So, I can also switch this, okay. If I switch phi h phi x and then minus plus the bracket h x, which will be 2 phi x, okay. But h x will be minus. So, this will be minus this, and then you will have this minus here, that will add up here, and then you can take this minus phi x square minus phi y, minus phi x square phi y. So, again you just, okay, switch these two and then try to compute this, you will see that this will become 0. Okay, maybe I will leave it to you. If you keep the signs properly, and it will not be a problem. But maybe like there is another way one can do this without doing much computation. So, let me actually think about it. So, if you have this bracket x y. So, what is the thing that we have? So, if you take bracket x y, so that is x y minus y x. So, that is nothing but h. Okay. So, then c is nothing but what? C is, so let me drop this phi, because phi is actually kind of gives me headache. So, let us drop this phi. So, then it is nothing but x y plus y x plus h square by 2. So, if you use this relation, already you can add and subtract. So, it is going to give me, so you add y x and then you subtract y x. So, it is going to give me h plus h square by 2 plus 2 y x. Okay. So, this is somewhat very simpler form. Maybe one can use this simpler form to compute. So, let us compute what is C x. So, C x will be h plus h square by 2 plus 2 y x comma x. So, but this is going to be h x plus h square by 2 x plus 2 y x x. So, if you just compute, so h s is going to give us 2 x, and what is about h square by 2 x. So, again if you do the computation, so let us do it here, h square by 2 x minus x h by 2. So, now you can keep h by 2 here. So, then it is going to be h x. So, you add and subtract x y. Okay. So, then here also you can add and subtract. So, you keep h x minus h x h by 2. So, what you get? You get h by 2. So, this is going to be bracket h x. So, that is 2 x, and this is going to be as it is plus h by 2 h x minus this and this you can add up. So, this is going to be plus h x. So, 2 x h by 2, and then this is minus h x. So, h x h by 2. Okay. So, now you can see that some cancellations are happening. So, this h square by 2 bracket x is nothing but this 2 cancelled, h x, and this get cancelled with this, plus this 2 get cancelled, x h. So, then you have plus twice y x x. So, again you compute the bracket y x x. So, that is going to be y x square minus x y x. Okay. So, here again you can replace this h x minus plus 2 h x. So, that is going to give me C x equal to, so this is going to be plus 4 x and then plus 2 x h and then plus this y x square minus this. Okay. So, but if you actually replace this y x minus x y x. Okay, let us do this y x minus x y x plus x y x. So, that is what I am going to add and subtract. So, then this is going to get cancelled with this. Okay. So, this is going to be h x. Okay. So, then 4 x plus 2 x h. So, sorry, this is y x minus h x. So, now if you replace this, okay. So then what you get? You get 4x plus 2hx, yeah, minus 2hx plus hx. So this is going to be twice bracket minus this, okay. Yeah, I guess I am getting one hx extra. Maybe I missed some calculation. So this is going to be minus 4x. So this is going to get cancelled, but this hx I am getting extra. I don't know why. So maybe I just missed some 2 somewhere. So if this is 2, then we are done. Okay. So why that is 2? Maybe it's hidden somewhere. Okay. So it is simply calculation, nothing else you can actually verify, not a problem. So I will actually move ahead. So only important thing is this is going to be inside your yeah, this C that we have defined, it is going to commute with the action of sl2 C. So in particularly this is going to give us some eigenspace decomposition, okay. So that eigenspace decomposition we will actually try to understand and then see what happens with. So if you start with this irreducible representation, then what happens? So if you take finite dimensional irreducible representation of sl2 C, so then you can see that this element that we have actually written, this C is nothing but what? So this is x y, okay, let me recall this new version. So this is yeah, h plus h square by 2 plus 2 y x. So that is our new element. Maybe we can write it as this also, not a problem, x y plus y x plus this h square by 2. Okay. So now you just apply it on V naught and then see what happens. So recall what is that V naught. So V is nothing but V naught plus V1, sorry, the span by this V naught, etc. Span of V naught, V1, etc. Vr, okay, if this is equal to V of r. So then you know that h V naught will be r V naught and then x V naught will be 0. Okay. So using that you can actually calculate what is C V naught. You can see that C V naught is equal to x y V naught plus y x V naught plus h square by 2 V naught. So then what it is? So x is going to kill. So it is going to give me just x y V naught plus h is going to give me d square by 2 V naught. But x v1 we know already how it is. Okay. X v1 is nothing but d times v naught. So if you use that, then you get C v naught is nothing but d square by 2 plus d v naught. Okay. But what is Schur's lemma says? Schur's lemma says C commutes with this action of G. So C is actually G module map from V of D to, sorry, V of, here I have written as R. Okay, let us switch this to D. So C is going to give me map from V of D to V of D. So which is a G module map. So using Schur's lemma, we see that this C has to be some identity times, some lambda times identity times V. Okay. So, in particularly if you are interested in calculating what is this lambda to be, you can calculate it from this equation. Okay. So, in particularly what will be lambda? So, lambda will be exactly d square by 2 plus t. So, that is the lambda. So, basically our calculation tells that this Casimir element acts very specifically on this given d plus 1 dimensional irreducible representation, which is exactly d plus d square by 2. Okay, I will stop here because we are running out of time. I will continue in the next lecture the proof of this complete reducibility. Thank you.